Multiple regression is the appropriate statistical tool when your response variable is quantitative. If your response variable is categorical with 2 levels, we need to use another multivariate tool, Logistic Regression.
Let's use the NESARC data for an example. We will use the same stats model formula library, which we imported as SMF. The function that we will use is the logit function. Our response variable, nicotine dep, is binary, coded 1 equals yes or 0 equals no to nicotine dependence, and so we should use a logistic regression. We also have an explanatory variable called SOC-PD-Life that indicates the presence or absence of social phobia, which is an anxiety disorder marked by a strong fear of being judged by others and of being embarrassed. First, we create an object called LREG1, which will include the results of our logistic regression model. Then we type an equal sign and then the function to run the logit regression, smf.logit. In parentheses, we type our formula and the name of the data set, sub1, and .fit followed by open and close parentheses, the same way we would for linear multiple regression analysis. Then we ask Python to print the fit statistics for the logistic regression model. Let's take a look at the output here. Similar to the multiple regression output, you can see the number of observations with complete data that were used in the model. Here we see the name of our response variable, nicotine dep. Also similar to the multiple regression output, we see a table with the parameter estimates and the p-value. Notice also that our regression is significant at a p-value of less than 0.0001. Using the parameter estimates, we could generate the linear equation. Nicotine dep is a function of 0.38 plus 1.23 times SOC-PD-Life.
But let's really think about this equation some more. In a regression model, our response variable was quantitative, and so it could theoretically take on any value. In a logistic regression, our response variable only takes on the values 0 and 1. Therefore, if I tried to use this equation as a best fit line, I would run into some problems. Instead of talking in decimals, it may be more helpful for us to talk about how the probability of being nicotine dependent changes based on the presence or absence of social phobia. For example, are those with social phobia more or less likely to be nicotine dependent than those without social phobia? Instead of true expected values, we want probabilities.
Described visually, we'll no longer find the best fit line, shown in red, very helpful to us, as our outcome variable cannot take on any value. Instead, we're saying that there is somewhere along our x-axis where our outcome variable moves from being more likely to be a 0 to being more likely to be a 1. Our goal will be to quantify the probability of getting a 1 versus a 0 for a given value on our x-axis.
In order to better answer our research question, we will choose odds ratios as opposed to coefficients. The odds ratio is the probability of an event occurring in one group compared to the probability of an event occurring in another group. Odds ratios are always given in the form of odds and are not linear. Odds ratios are often a confusing topic for students when they're first introduced to it, so it will be important to go through it conceptually and better understand exactly what an odds ratio is and what it means.
An odds ratio can range from 0 to positive infinity and is centered around the value 1. If we ran our model and got an odds ratio of 1, it would mean that there's an equal probability of nicotine dependence among those with and without social phobia. Those with social phobia are equally as likely to be nicotine dependent as those without. It's also likely then that our model would be statistically non-significant. If an odds ratio is greater than 1, it means that the probability of becoming nicotine dependent increases among those with social phobia compared to those without. In contrast, if the odds ratio is below 1, it means that the probability of becoming nicotine dependent is lower among those with social phobia than among those without.
So how do we calculate the odds ratio? It is possible to do this by hand. The odds ratio is the natural exponentiation of our parameter estimate. Thus, all we would need to do is calculate the natural log to the power of our parameter estimate. However, we could also let Python do this for us by adding the following Python code. First, we ask Python to print the title odds ratios. Then in the second line of code, we ask Python to print the odds ratios, which are computed using the numpy.exp or exponentiate function. In parentheses, we add the object that contains the parameter estimates, PARAMS, from our LREG1 model. Here are the results. Because both my explanatory and response variables in the model are binary, coded 0 and 1, I can interpret the odds ratio in the following way. Young adult daily smokers in my sample with social phobia are 3.4 times more likely to have nicotine dependence than young adult smokers without social phobia. We can also get a confidence interval for our odds ratio. Remember that our dataset is just a sample of a population. We do not have every young adult daily smoker in the U.S. in our sample. Even though the odds ratio for our sample is 3.4, the true population odds ratio might be slightly different due to random variation in sampling. The code to print the confidence intervals for the odds ratio is here. In the first line of code, we create an object called params, P-A-R-A-M-S, that includes the parameter estimates from our LREG1 logistic regression model. In the second line of code, we create an object called conf that uses the stats model conf_int open and close paren command to return the confidence intervals for the parameter estimates. In the third and fourth lines of code, we create an odds ratio object with column labels of lower CI, upper CI, and OR. Finally, print the confidence intervals using the numpy.exp function to compute the odds ratios from the parameter estimates in the conf object. The odds ratio indicates that there's a 95% certainty that the true population odds ratio falls somewhere between 1.78 and 6.61.
It's important to keep in mind that the odds ratio is simply a statistic calculated for the sample. So looking at the confidence interval, we can get a better picture of how much this value would change for a different sample drawn from the population. Based on our model, those with social phobia are anywhere from 1.78 to 6.61 times more likely to have a nicotine dependence than those without social phobia. The odds ratio is a sample statistic, and the confidence intervals are an estimate of the population parameter.